Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is Kim Ricketts, and I'm here to introduce and welcome James Kakalios, who is visiting us as part of the Microsoft Research Visiting Speaker Series. James is here today to discuss his new book, The Amazing Story of Quantum Mechanics. Science has met more demands of science fiction than most people realize, thanks to quantum mechanics. Though we don't see the world of the Jetsons with flying cars, people getting to work by jetpack, or Star Trek's teleporters yet, we do have smartphones, pocket-sized computers, and hybrid vehicles. Because of quantum mechanics, we may also see many more science fiction technologies become a reality. James is a professor in the School of Physics and Astronomy at the University of Minnesota. He served as a consultant for the film Watchmen and won a regional Emmy Award for his role in The Science of Watchmen. He is the author of the critically acclaimed The Physics of Superheroes. So please join me in welcoming James Kakalios to Microsoft.
Thank you very much. Thank you for the introduction. Thank you all very much for inviting me and welcoming me. I must say the working title of my new book originally was The World of Tomorrow, and so it's kind of a pleasure to come here and see the guys who are actually responsible for that. Actually, Microsoft seems to be following me. 2 weeks ago, I was in New York for some media events, and walking around Times Square at night, seeing these huge throngs of people lined up. And what movie or concert are they going to? No, they're waiting for the Kinect to go on sale at midnight. So I assume that you just like give one out to the speakers, but I want to talk about The Amazing Story of Quantum Mechanics, my new book. First, let me give you a little bit of background. How did a mild-mannered physics professor get associated with comic book superheroes, Spider-Man and Superman? In my day job, I'm a condensed matter experimentalist. So I do basically solid-state physics. I've been doing this for over 20 years, doing research on amorphous semiconductors. You know, this is silicon, amorphous silicon used in solar cells or flat panel displays, thin film transistors. Done a lot of work studying electronic noise in these materials. For about 10 years, I've studied sand piles. Sand was quite hot in physics there for a while. We call it granular media when we talk to the funding agencies. And most recently, collaborating with professors in neuroscience, using techniques that I developed to study electronic noise in disordered semiconductors and applying them to voltage fluctuations in the brain. But that's not why I'm here. I'm here because back in 2001, I created a freshman seminar class at the University of Minnesota called Everything I Know About Science I Learned from Reading Comic Books, which my colleague said explained a lot. This is a real physics class that covers everything from Isaac Newton to the transistor, but there's not an inclined plane or pulley in sight. All the examples come from superhero comic books, and as much as possible, those cases where the superheroes get their physics right. Now, obviously, the superpowers themselves are impossible, but once you grant a one-time miracle exemption from the laws of nature, what they're shown doing with their powers is scientifically correct. I showed this cover here because this was actually a comic that I bought as a kid, even though I wasn't a big fan of Superman at the time, because Superman is here visiting a college campus, and I was just fascinated to find out what life in college was going to be like. Even as a kid back in the 60s, I knew that this part wasn't too accurate. But there are things here on the cover that, as you all know, turn out to be correct. Namely, all professors at all times always wear caps and gowns. And all professors are 800-year-old white men. But from this class, then in May of 2002, I wrote an op-ed that was published in the Minneapolis Star Tribune pointing out how a key scene in a classic Spider-Man comic book turns out to be a textbook illustration of Newton's laws of motion. I thought, well, the Spider-Man movie is about to open, the first one. And so this might be a good opportunity to get some science into the newspaper. The University of Minnesota put out a little press release saying, well, Spider-Man's on the big screen, but if you want to know about the science of superheroes, the person to ask is Jim Kakalius, teaches this freshman seminar, blah, blah, blah. I should point out that they've sent out press releases about me before, about my work on amorphous semiconductors or 1 over F noise. Result? 0. Yes. You write one story about Spider-Man, however, and the movie opened on Friday. The op-ed appeared on Friday. By Monday, I was getting calls from the BBC, the London Times, CNN Headline News. The Associated Press came to my office, where I just happened to have these lecture demonstration tools on hand. That was a lucky break. At this stage of my life, I've reconciled myself to the fact that I can win 3 Nobel Prizes, and I know what photo they're using in my obituary. My colleagues say, win 3 Nobel Prizes, like how, on eBay? This article actually went across the nation. This is a clipping from the Chicago Sun-Times. It actually went around the world. I think I know what they're saying about me here, in a Turkish clipping. And then I started showing up in places that physicists don't usually appear. So, if you're ever playing Trivial Pursuit, and you're playing Volume 6, and you get card 291, I'll tell you right now, the science question, the answer is kryptons. The question is, what planet's gravity did science professor Jim Kakalius estimate by calculating the force needed to leap over an Earth building in a single bound? Now, I didn't even know about this. One of the graduate students came to me one day and showed me this card, brought this to my attention. I borrowed the card, brought it downstairs, showed it to my department chairman, and I said, Alan, who's the most famous scientist you know? And he looked at the card, and he looked at me, and he said, Stephen Hawking. Who's not a genius? Oh, well, then it's you. And so in 2005, one of the nice things about all this attention was the receiving hundreds and hundreds of emails from students and teachers and people long out of college who liked this idea of teaching science using comic books, asking if I had a book, which eventually led to my writing a book, which is now out in a second edition. And that has led me to the current talk, in the current book, talking about the amazing story of quantum mechanics that I want to talk about today. Because there is also a comic book connection to this. You know, reading comic books, they all predicted what life was going to be like in the future. Here's an old adventure comics where Superboy goes 1,000 years in the future and meets these other superpowered teenagers, the Legion of Superheroes. And this was a very popular feature, and he constantly, by being able to break the time barrier, would go 1,000 years into the future and have adventures with the Legion of Superheroes. And in the future, it was promised that we would be in a better place. And the reason we'd be in a better place is thanks to science. In the 1,000 years from now, if you got in trouble, you wouldn't call for the police, you called for the science police. Here in another comic, one of the Legionnaires is falsely accused of betraying the Legion, and so they lock him up, and he's got this computerized device that provides the 3 necessities of life: food, water, books. But really, this goes back even further. Here's from 1928, the first appearance of Buck Rogers in the science fiction pulp magazine Amazing Stories. And they promised us that in the future we'd have jetpacks, flying cars, robot domestic assistants, underwater cities, when what we got instead were cell phones, laptop computers, DVDs, magnetic resonance imaging. So some guys are reluctant to give up on the jetpack. But we do have jetpacks, right? And you can take a jetpack to work. provided you live just a couple of blocks from where you work. Because the problem is, the writers of the science fiction pulps and comic books thought that we'd have a revolution in energy, which is necessary in order to have like flying cars and death rays, when what we got instead was a revolution in information. And energy, you're pretty much limited to the chemical bonding strengths between atoms and molecules. And, you know, for the physicists in the audience, that's on the order of a few electron volts. That's the energy scale. Visible light, red light has an energy of about a little under 2 electron volts. So that gives you the sense of the energy. Very few people, in order to have enough energy to take an extended trip or to levitate a car, you'd need like nuclear power, which produces millions of electron volts per reactant. But few people are willing to have an unlicensed nuclear power pack on their backs, unless you're a member of the Ghostbusters. But it was promised that we might have, you know, nuclear power in our day-to-day lives, thought back in the 50s. This is the 1957 Ford Nucleon, the prototype of a nuclear car. They never built it, but it would have a little a fission reactor with a little mini cooling tower here, with tail fins larger than the car even. And the idea is that you could go 5,000 miles before you'd have to swap out the nuclear core. What you do in the case of a fender bender was never really talked about. But there's actually an interesting convergence between the science fiction future and the real future that we had. Hugo Gernsback first publishes Amazing Stories, the first pulp magazine devoted to science fiction, in April 1926. Also publishing in 1926, Erwin Schrödinger, publishing his equation, the Schrödinger equation, which would serve as the foundation for modern quantum theory. Schrödinger and a handful of other scientists developed quantum mechanics because they're trying to understand how atoms interact with light. A generation later, groups of scientists at Bell Labs and other research laboratories developed the laser and the transistor. You don't accidentally discover a laser. Right? You have to go into the lab and willfully, with malice aforethought, go and build such a device. And you can't do it without an understanding of how atoms and light interact, provided by quantum mechanics. A generation later, you get CD players, personal computers, laptops, cell phones, everything my teenage children would say, without which life is not worth living. None of these are possible without the transistor and or the laser, neither of which are possible without quantum mechanics. This is pure, well, nowadays we would say that this is curiosity-based research. Right? Schrödinger is just trying to understand how the world works. Schrödinger, Heisenberg, Pauli, Bohr. If you went to him and said, "Nice equation, Erwin, what's it good for?" He's not going to say, "Well, if you want to store music in a compact digital format." But really, without the insights provided by a handful of people, the world we live in would be profoundly different. For example, we'd still have computers, but they'd use vacuum tubes. So to have a computer that has the same power as a laptop, you'd have to be about the size of a room. So there'd be very few of them. Only corporations and the government would own them. There'd be very little reason to link them together in an internet. There'd be no World Wide Web. So there's all sorts of things that the world has changed that we don't really think of. I think I once figured out that in an average hospital, there's probably more transistors than there are stars in the Milky Way galaxy. So we don't notice how often this comes about. So this all came about thanks to semiconductor and solid-state physics, which was enabled due to quantum mechanics. How many people don't know quantum mechanics here? Great. That'll change by the end of the talk. I have about 40 minutes to teach you all quantum mechanics, which leaves me with a problem. What am I going to do with the other 35? Right. It has a reputation for being weird and incomprehensible. The ideas are certainly weird, but they're no weirder than saying that we live in a sea of invisible electromagnetic waves. Only a small slice we can actually detect. We never think about that unless you can't get 5 bars on your phone or your laptop. And then you notice that the sea is missing. So let me boil it down to understand how quantum mechanics leads to something like a laser. Let me boil it down to 3 things, like in a comic book, 3 suspensions of disbelief, 3 things that you'd have to buy into. That light has both a wave and particle-like property associated with termed photons. Matter has both a particle and wave-like properties. And that everything, light and matter, has an intrinsic spin. Okay. This is all, if you buy that, this has nothing to do with wave indeterminacy or the measurement problem or Schrodinger's cat. I'm taking what I describe as a working man's view of quantum mechanics. This is the stuff that we experimentalists make use of when designing semiconductor devices. So let's look at the first principle. Light has both a wave and particle-like property, photons. A manifestation of that is that when you shine light on a metal, if light was just a continuous series of waves, like washing up on a beach, the waves might eventually push some pebbles up the slope of the beach. But really what the light is composed of is a machine gun bullet spray. And by changing the frequency of the light, the frequency would just be the spacing between the crests. And that would just determine the rate at which the pebbles are advanced. But the frequency actually controls the energy of the bullets. And so by increasing the frequency, we can have bullets that can promote the electrons out of the material. This is called the photoelectric effect. There are, of course, practical applications to this that we all know, right? That you can get photons in this way. Matter has both a particle and wave-like properties. One of the most striking examples of this is interference. That's the hallmark of wave phenomena. You have a wave striking a surface and it gets reflected, but maybe part of it passes through and reflects off the bottom. And if these 2 waves are in phase, they would add up coherently and we'd get a very strong signal. But if they come in out of phase here, then they would add up destructively and cancel out. And so when you look at an oil slick on a wet driveway, the oil slick floats on the water and creates a freestanding film. And if it's not too thick, some of the light can be reflected from the top or pass through and come out. Because the oil slick is not a uniform thickness, some regions might have a thickness such that some colors add up coherently and we'll see the red light out of the white light that's striking the surface, whereas the other wavelengths interfere destructively and cancel. And then we might get blue light over here and so on. And this interference pattern is a hallmark of the wave phenomena. If I pass a laser light through a screen, I can get an interference pattern. By choosing the grid of the screen, I can get this nice circular with dot pattern. But if I send electrons on a crystal, electrons have a wave-like nature that's associated with their momentum. We don't notice our wave-like aspect because we're made of lots of atoms. So we have, even moving very slowly, we have an enormous momentum compared to an electron. The bigger the momentum, the smaller the wavelength. If I walk across the room, the momentum of my matter wave is a trillionth smaller than the nucleus of an atom. It's impossible to detect. There's no way to see such a thing. For an electron inside an atom, its wavelength is about the size of the atom. It's impossible to ignore. And that's why this wave-like nature only became evident when studying the properties of atoms in detail back in the 1920s. You choose the momentum of the electrons correctly, and they scatter off the atoms in a crystal. And, well, if the room were darker, you could actually see this a little bit better, but you see the same type of ring pattern with the spots. that I saw, this is for laser light, and these are for electrons. So you have the same interference pattern for matter or light. And then the last part is that everything light and matter has an intrinsic spin. Of course, those who look at those old pulp magazines know that. Every month had an application of spin. But I'm actually more talking about the spin, say, like of a twirling ballerina. Even that is a bit of a misnomer. It's not as if the electron were actually rotating like a top, but this is still the phrase that's used. This rotation is also associated with a magnetic field that has both a north and south pole. And we know a north and south pole, the magnetic fields flow out of the north and into the south. And so that means that electrons can have magnetic fields that can point in two directions. It can either have a north pole down here, or it can have a north pole here. Because the charge of the electron is negative, the magnetic field lines are drawn in the opposite direction. That's a technicality that we don't have to worry about, but there's basically two ways to... Every electron, in addition to having a mass and an electric charge, has a little built-in magnetic field. And that magnetic field can point up or it can point down. And that's all we need, right? So that took about 5 minutes. Okay. So now you're all masters of quantum mechanics. So now we can... and that magnetism is also very important, at least a lot of practical applications. We know from Dick Tracy comic strips it'll give us flying garbage cans. And I love this notion, the nation that controls magnetism will control the universe. But this internal magnetic field that electrons, protons, neutrons have actually enables us to, we can do things like we can store information on hard drives this way. In the movies, Ray Milland had to take a serum in order to as a doctor, in order to diagnose people and see inside their body. Now we have magnetic resonance imaging. And that's made possible by making use of this internal magnetic field that the nuclei of all atoms have. And so it is impossible without quantum mechanics. If you saw this in a 1930s movie, you'd say, no way. Did someone just go into this cylinder and the doctor sees inside them and can diagnose what has a tumor and what isn't, right? And now it's a standard diagnostic tool. One of my colleagues at Professor Bruce Hammer at the University of Minnesota, as a favor, used his MRI and did a scan. Does anyone recognize what these are?
Peanut butter cups?
Yep, Reese's peanut butter cups. Yep. So, the surprise inside. Yeah, you could just foolishly bite into it, but thanks to science, right, we can verify. So, how do we combine these three principles to explain how atoms interact with light? Let's first make use of the second principle, that matter has both a particle and wave-like nature. For the electrons inside the atom, that puts constraints on the possible waves that can exist. We're used to there being constraints on possible waves. Think about a guitar string. It's clamped at both ends. So if I pluck it, it can vibrate, and I might get this type of a wave that could be created, but I could not get this wave because it's not clamped at the end down here. It would be moving. So this is not allowed, but this is an allowed wave. If I have an electron that goes around in a circular orbit around a nucleus, this constraint means that there are certain waves that fit exactly in and create nice standing wave patterns. But there might be other waves that don't. And they can't exist because it doesn't make any sense to talk about a wave that doesn't join up smoothly. But since I said that the wavelength is associated with the momentum, and the momentum is associated with the energy, that means that the electron can only have certain energy values inside the atom. And so when you look, and then you ask, what does that do in terms of how the atom then interacts with light? Now we make use of the fact that the energy of the light comes in discrete packets of energy as photons. So when the electron in the atom moves from one orbit to another, it emits a photon of energy that has a color characteristic to that transition. And every atom has its own fingerprint, so that there's a series of possible wavelengths that are observed for hydrogen and a different series for sodium. This also explains why sodium street lamps have a yellow tinge. Right? Helium looks a lot like hydrogen, but there's a line that hydrogen doesn't have. Helium was actually discovered by looking at the spectrum of light emitted from atoms in the sun. That's why it's called helium, after Helios, the sun god. So for a long time, scientists thought that maybe this is an element that only existed in stars until it was discovered on Earth. Before it was discovered on Earth, there was no helium. The people didn't know about it. So they would just drag the deflated balloons on the Macy's parade up Broadway. It was kind of a pointless exercise. But anyway, neon has a bit of a red tinge. Mercury, every element has a unique fingerprint of different wavelengths. And this was known for at least 30 years prior to being understood with the introduction of quantum mechanics. This was one of the main pushes to develop quantum mechanics, to explain this. And whenever people say, well, some aspect in biology is too complicated to actually, you can't explain it, right? Not being able to explain something, is a feature, not a bug. It's if we understood everything, I'd be out of a job. So this is, but eventually it was understood. If you want another example of these line spectra, back in the 1950s, you take out as DC Comics' Strange Adventures, where a scientist here is amazed to discover that his spectrogram plate shows colored lines are caused by various elements, and this line reveals the presence nearby of a radioactive metallic element hitherto undiscovered in the entire solar system. I love this for two reasons. One, this is in fact what a line spectra looks like. This is in fact how you would, like the discovery of helium, discover a new element. And why doesn't anyone use hitherto anymore in everyday conversation? And he's thinking it to himself in complete sentences. You could maybe say that the comic books back in the 50s were corrupting kids' minds, right? Because isn't that what literature is supposed to do? but you can't say it wasn't improving their vocabulary. Now, this picture of these orbits and the transitions is so appealing that it's a pity that it's not right. This was the motivation for Schrödinger to develop the Schrödinger equation, because basically if the electrons were orbiting a positively charged nucleus, they should emit energy continuously in a continuous spectrum of light. And since light carries energy, they should lose energy, slow down, and eventually within actually a trillionth of a second, all electrons should just spiral into the nucleus. That would be a bad thing. So to understand why that doesn't happen, Schrödinger basically developed what is, it certainly doesn't look like it, but it is in essence force equals mass times acceleration for electrons in atoms. It says, you tell me the forces acting on the electron, and I'll get this function here, psi, and if I square psi, it tells me the probability of finding the electron at some point in space and time. And what you find is that there's actually a series of different wave probability distributions. Each one has its own energy. And the electron can only be in one possible wave at a time, one different wave function at a time, but each one has a different energy, and you can then calculate things like what's the average radius, the energy, the angular momentum of these electrons, and the calculated values and the measured values agree exactly. So basically Schrödinger says that for an electron in an atom, these different possible wave patterns are analogous to a series of chairs in an auditorium. The positively charged nucleus is the front of the room, and there's a seat, and then at a higher energy, a little bit further back in the next row, there's another seat. And then there's another row that's got 3 seats. Why? Doesn't matter. Another seat, 3, 1, 5, 3, and so on. And the electron can only sit in the seats, can't stand in the between rows. And so when you have hydrogen, say, it can move, if I give it some energy, it can move from one row to another and then emit energy as it moves down. You put in the nature of the forces acting on the electron with the positively charged nucleus, the proton. The force is known, it's electrostatics. And you get exact agreement with the measured line spectra. Okay? So we understand hydrogen. Now I need my third principle in order to understand something a lot more complicated, like 2 electrons. Okay? What happens if I have 2 electrons? Then I make use of the fact that everything light and matter has an intrinsic spin. If the electron's in an intrinsic spin, how does that influence when the 2 electrons are so close that their waves overlap, like in, say, helium? Well, the Pauli exclusion principle states that if 2 electrons are in the same quantum state, they have to have opposite spins. Basically, the magnetic fields have to be opposite. That's the lowest energy configuration. Not even the lowest energy. That's the only allowed configuration. Anything else cannot happen. Well, anything else, the Schrödinger equation says the probability is 0. Not small, but 0. And if the probability of something happening is 0, it never happens. It's forbidden. So I have hydrogen, and I want to add another electron to helium, and it could sit in the front. These seats, it turns out, are actually love seats. Okay? And actually kind of like the old curvy kind, so they fit facing away from each other. But now if I have something more complicated, like 3 electrons in lithium, it's got to go sit in another seat because this can either be spin up or spin down, but then it would be the same as this one here, and that the probability is 0. Carbon has 6. Aluminum has 13. And so now we start to see why chemistry. These arrangement of the rows come out of the Schrödinger equation. What's the force acting on the electrons? Electrostatics. It tells me the arrangement of the seats. If I change this positive charge, the spacing between rows will change slightly, which is why each atom has its own unique spectrum of light that's given off. And then we can understand why some atoms interact chemically with other atoms. Say we could go back to carbon, and these 2 electrons and these 2 electrons frequently can remix. And then if I have one of these electrons in one carbon atom and another electron with another carbon atom, they can actually form their own little love seat in a chemical bond. And we have here, if they form 4 chemical bonds in the same direction, we have diamond. I can make use of quantum mechanics. Also, I just want to show this. I can make use of quantum mechanics to actually see where the carbon atoms are by bringing a metal tip very close to an atom. And when it's very near, some of the electrons can actually have a probability of being in the tip and being recorded as a current. And when there's no atom, there's no electron, so there's no current. And so I can use this to image where the atoms are. So this is carbon again, only the stronger form of carbon. This is graphite. If you had it 1 atom thick, you'd have a Nobel Prize, and you'd have graphene. And graphene is extremely strong. Actually, the bonds in graphite in the plane are stronger than diamond bonds. Between the plane, they're extremely weak, which is why you can use it for a pencil. You just push the pencil, and you unroll the graphite layer by layer. And it's held onto the paper by electrostatics, which is why you can erase it easily. But you could take graphene, roll it up into a carbon nanotube. If you had enough of these tubes that you could braid them together into a little fiber, then if the fiber is no larger, the diameter, than the period at the end of a sentence, it could still hold up 2 SUVs. So if you could mass produce this in large quantities, that's your cable for your space elevator right there. I gave you that idea free. Nobel Prize, please. Here's a better image that shows this nice hexagonal pattern of the carbon atoms here. Of course, we'd like to eventually get something a little bit larger than a single electron to go through a barrier, even if the barrier is just a vacuum of empty space. Of course, if we ever get something larger than electrons, we know that comic books will have been there first. Here's a nice example from the 2000 movie X-Men. Oh, not this one. Not that one. Oh, and they put it into mute. That's too bad. Oh well. That's a pity. Here's Kitty Pryde, who can adjust her quantum mechanical tunneling probability at will. And I swear to God, if you go back and watch that scene, at the very end, he holds up the textbook and says, physics. Getting back to physics, let's look at comparing either carbon or aluminum, and let's look at those last rows and whether the last rows are completely filled with electrons or the seats have only one electron in them. I bring a trillion atoms together and I form a solid. And they're all chemically bonded to each other because otherwise it's a gas. So they all are forming chemical bonds. And the question is, do all those seats that then broaden into an auditorium, is every seat in the auditorium occupied? Or is it like aluminum, where there's still a lot of empty spaces? So every seat in the auditorium, only half of them are occupied. This is what I'd call a metal, and this is what I'd call an insulator. Because if I applied an electric field, here the electrons want to move, they want to gain energy, they get accelerated by the electric field, and there's a space for them to go. There's a high energy space. I shine light, the electron can go up here, and then it drops down, or it could go up to here and drop down. It doesn't matter what color light I shine, I get the same light back. Metals are shiny for that reason. They're good conductors of electricity and heat. An insulator, remember there was lots of other rows that just didn't have electrons in them. The next row up broadens into a balcony that's ordinarily empty. I have to provide energy to push an electron up here. Now it can carry electricity. Remember that you can only absorb light if there's a place for you to go. So that's why I can look through a window, because the gap between the last filled state and the first empty state is in the ultraviolet. So the visible light passes right through. So we understand why we can see through things. You add magnesium or chromium and you could stain the glass because you put a little seat right in the middle that some light can be absorbed by. So we understand materials thanks to quantum mechanics. So here again, this is showing that if I actually promote an electron up into the balcony, I leave an empty seat behind, and these empty seats can also carry electricity. Because then if an electron hops into the empty seat, I can think of it as the empty seat moving around. So I can conduct electricity two ways here. So in the next 10 minutes, I'll tell you about how lasers work and how that leads to CDs and Blu-rays. So, armed with this understanding, scientists working very hard in the late 50s, early 60s, developed the laser. As soon as it was developed, they held press conferences. First question, is this a death ray? This is serious. Bell Labs press department would brief the scientists, don't say death ray, don't mention death ray, right? Good luck with that. First thing in the papers, scientists invent death ray. This is not a death ray. This is a death ray. This is an interesting showing how science goes over to pop culture. This is Ted Maiman And this is the first laser that he constructed in 1960. 4 years later, there's a practical application of lasers in Goldfinger. Right? 64. The first lasers built in 1960. That shows you how primed everyone was to believe that it was a death ray, that it shows up instantly in bisecting 007. Obviously, I just learned this a couple of months ago. This obviously was just like, colored in on the film. But remember, in the scene, the metal thing is melting. Apparently there was a guy underneath it with a blowtorch that was moving up there. I assume they had like this little, with masking tape, this X. Said, don't go past here. Oh, you want to renegotiate your contract, Mr. Bond? There you go. Oh, and I want to point out, again, this is going back to the old pre-superhero comic books. I know there's competition between different research labs. And there certainly was back in the late 50s. Here's Charles Towns and Mayman, Towns at Bell Labs and Mayman at Hughes Research Lab. There was a big race and a big competition to discover the laser, to build the first laser. But, the comic books show that sometimes this competition can be quite nasty. In particular, if you're looking at Tales of Suspense number 22, it tells about this giant monster, Brutu, who actually was a mutated, transformed young scientist. He was smaller and skinnier than all the other fellows, and here in college, he's being picked on by bigger fellows. But, he studies, he works hard, and he eventually becomes a scientist in a research lab. Think his life is any better? Here he is. But even when I was a scientist working in a laboratory, my skinny frame provided others with amusement. Howard ought to work on vitamin pills. He might discover one that'll help him grow into a man. Oh, this, careful, he's liable to hear you. Then he'll start another fight and you'll have to beat him up again. So I don't know what goes on here in Microsoft, but things used to be pretty tough. This Brutu, this was out of Marvel Comics before they started publishing Fantastic Four and Spider-Man, and they put out a series of comic books that every month Earth was being attacked by some giant monster from another planet, another dimension, lost in time. You have Journey into Mystery, and I always first person. I battled Rorg, king of the spider monsters. Here, Tales to Astonish. I challenged Groot, the monster from Planet X. And in all of these stories, the local law enforcement was useless. The military couldn't stop them. Earth was traditionally saved only by the efforts of a lone scientist. And we see at the end of the Groot story in particular, here we have the sheriff and he's chagrined. Well, I never even thought of that. That's why Evans is a scientist and you're only a sheriff. And I love this here. His wife embraces him. Oh, darling, forgive me. I've been such a fool. I'll never complain about you again. Never. Personally, I can't tell you how many times I've heard that from my own wife. Primarily because it involves imaginary numbers. But it's a good thing that scientists were on the case. Because it wasn't just Rorg and Groot. Every month brought a challenge, whether it was Lokar, Orgo, Moomba, Rambu, Gruto, Grog, Gugam, son of Goon, and Fin Fang Foom. And then one month saw the scariest monster of all, the tax collector from outer space. But back to the laser, we stake a material that ordinarily would be an insulator. It has a filled orchestra and a completely empty balcony. And we're going to add a row of seats, either by adding a chemical impurity, such as some phosphorus atom, or because it's natural in the spectrum of the helium or neon atoms. We add a row of seats right below the balcony, a mezzanine. And then we're going to fill that mezzanine up with electrons, but of course the electrons can only come from the orchestra. That's the only place that I can bring them. So if I shine light on the material, now the mezzanine, the trick is that it's hard to put electrons here, but then that means that it's hard for them to drop back down, so it's hard to get in, but hard to get out. So most of the light gets absorbed up to the balcony. Some of them fall down into the mezzanine where they stay for a while. And then even once you've turned the light off, there are still these electrons in the mezzanine, and eventually they fall down into the open seats in the orchestra. They emit light when they do. And you know what I've described here, a glow-in-the-dark toy. Right? Which I'm sure there was a point in your life where this was the greatest technological achievement in the universe. Or you can have, so there's basically only two ways the electrons can fall down from the mezzanine to the orchestra. They can fall on their own, one at a time, like in a glow-in-the-dark toy, or they can be pushed, like a laser. In a laser, one photon in stimulates the emission of many photons. It basically causes one to fall, which then triggers the next one, and they all start falling, and it goes at the speed of light, so you don't see any time delay. They all come down at the same time. They all emit light at exactly the same energy, so it all has the same color. They all do it at the same time, so they're all coherent. All the waves add up coherently. You arrange it so that they all go in one direction, and you get a laser. Yeah. Here we see from a page from Dr. Solar, Man of the Atom. Light amplification of the stimulated emission of radiation, or a laser. Birth of a death ray. But really, one of the most practical applications is in storing information on these small little shiny disks. They're actually quite compact. On the disk are a series of scratches or pits. And this is how the ones and zeros are encoded. Now, this is an oversimplification of what goes on inside the CD, but it has the basic element of it. When a laser bounces off one of the shiny parts, it's deflected to a sensor, and that can be defined as a 0. But if it strikes one of the edges of the pits, it's deflected away, and that's recorded as a 1, excuse me. So you can encode ones and zeros from the spacing of the pits. By changing the color of the light, you can change the wavelength. But in the 1980s, you could only mass produce efficiently infrared lasers, solid-state infrared lasers. The wavelength is quite large, so the size of the pits has to be big. And the size of the disk was chosen back in the 80s to be large enough to encode the information for Beethoven's Ninth Symphony. That was the definition. That was what the engineers set up, so that you could do it all on one disk. You could encode the information for images and sound, but then you needed a bigger disk. And so you had these laser disks, these 12-inch disks back in the 80s. But by the 90s, red light lasers were the materials issues. I mean, the physics was known. It's a question of just the technology, which is non-trivial, of course. Have a smaller wavelength, so now you can have the pits smaller, that you can pack them closer together. So now you can have both images and sound. And now we have blue light lasers, which is what the blue in Blu-ray stands for. And so we can have high def. And so we can replace 10 of these with one of these, thanks to quantum mechanics. So I leave you with this challenge. Because another aspect that we were promised aside from the Dick Tracy comic strips, aside from flying garbage cans, was the two-way wrist TV. Tracy actually was always in the vanguard of technology. In 1944, the two-way wrist radio was introduced. And actually, if you pop the top on this, you find a series of tiny tubes, which is kind of fair because the transistor wasn't invented until 47. So, you can't blame Chester Gould for not anticipating that you wouldn't need vacuum tubes, just really tiny ones. And then by 1964, the two-way wrist TV. And this is a bit of a challenge for you guys here, right? He's got the wrist TV, and he also shows all the schematics. Here are some of the features of it. The range has not yet been established, but we believe it to be nearly limitless. He's also managed the battery problem because it uses a powerful atomic bullet to feed the power. I don't know about the side effects. I do know that when he first put this on, this guy had no hair on his wrist. But this has been 1964. Where's the two-way wrist TV? Okay? But in December of 2008, there was good news. There was an announcement that LG was bringing out the Dick Tracy watch. An LCD screen, 4 lines of data here, right? So finally, we have beaten Dick Tracy. 1986? Right? Oh, well, with a liquid crystal display. The conclusion, it's Dick Tracy's world. We're just living in it. Remember, the nation that controls magnetism will control the universe. Thank you very much. I just want to point out that both Physics of Superheroes and Amazing Stories are available for sale, and they have them in the back. And so I have one last slide. Please concentrate on this message from the ringmaster of the Circus of Crime. Thank you all very much. And I'd be happy to take any questions. Yes, sir.
You mentioned that the electron's orbit does not decay, but you didn't say why.
Right, because it's not actually, strictly speaking, true to describe it as an orbit. The solar system picture of a nucleus that's like the sun and the electrons like the planets is actually not correct. It's a useful image to hold in your head. But really what happens is all you can actually say is that there's a probability of finding the electron in some wave pattern. And there's a characteristic energy associated with it. And if you give the electron energy, and if it's an allowed transition, it can go into another wave pattern that has a different energy. And when it goes from one wave pattern down to another wave pattern, it can emit energy in the form of a photon. But at no point do we actually know where the electron is. Quantum mechanics gives, the thing is, it's like a perfect theory, physics theory, because it gives accurate, correct predictions for anything we can measure, and for anything that we can't measure, it gives nonsense. It says, it's like, but I want to know where the electron is really. But you can't measure where it is really, so the answer is, shut up. No, because if I wanted to measure where it is really, how would I do that? Right? I want to see where you guys are really. I will find this out by shining light off of you. It will reflect from your body. I will see it in my eye, and I will see where you are. But I need to have the wavelength of the light has to be smaller than you are. Okay, that's not a problem. But to get the wavelength of the light smaller than an electron inside the atom means that I need very small wavelengths, which means very high energies. Remember the photons, that's now coming in with a very high energy electron, and it scatters the electron. I can tell you where the electron used to be, but not where it is. And that's the whole notion of the role of the observer. Right? Say I have a vibrating string and I can't hear it, but I've got like Daredevil and I've got super sensitive touch. So if you touch the string, I can tell you exactly the frequency of vibration. But of course now I've touched the string. I've changed the vibration. So I can bring myself closer and closer and I can feel the air vibrating and I can get a determination of the frequency. But of course the wave is now bouncing off my fingertips and is interfering with the string. So the more accurate my measurement, the more I'm disturbing the system and changing it. And so that's the whole notion of role of the observer and that type of stuff that enters into it. But at the end of the day, we actually don't, for most device work, we don't have to worry about that. Yes, sir?
So Dr. Feynman had tried to introduce quantum mechanics or physics for freshmen back in 59 and 60, I believe it was, at Caltech College. Are you using any? It didn't work out so well for him, but he did have a lot of grad students, I understand, stay with the course, and I'm sure you're familiar with that. Have you looked at that? I mean, is there a different approach that you're going at it, or what?
Well, this is yes. I mean, so Feynman did in a series of lectures that are collected in 3 volumes, the Feynman Lectures of Physics. He basically reimagines physics. Feynman is a true genius, in the sense like a genius. Like you go into a darkened room that you've never been there, and he describes where all the furniture is. You turn the light on, and it makes perfect sense what he said, but how would you know it before the light was turned on? But Feynman knew these things, and the way he understood physics was very insightful, but not very practical if you're learning it for the very first time. That was the problem he found. After you've already got a degree in physics, reading the Feynman lectures is a great thing to do. I could do everything else at 90 degrees rotated. What I've done, I've been teaching quantum mechanics to sophomores and undergraduates for many years. And so a lot of these analogies, like auditoriums and stuff like that, are things that I kind of have codged together over the years. But this book is not meant as a textbook. It's meant for a general readership that would like to understand, say, how magnetic resonance imaging works. How does a junk drive work? Because I explain how a transistor works. And then once you have that, you can explain floating gate transistors, you can explain junk drives. How does a television remote control work? As it is not meant for scientists and engineers. And I take some shortcuts at some point, and I have asked, a little footnote telling what the correct answer is, and saying, if you understood this book is not for you. It's not meant for scientists and engineers, but rather for anyone who's going to be a citizen and a voter. Because we are all called upon more and more now to have opinions on scientific and technological issues. Whether it's climate change or alternative energy or nanotechnology. And so I try to couch this in comic books and science fiction pulps because there's a great deal of insecurity on the part of non-scientists in their ability to understand this. If I describe my research to one of my colleagues and I do a crummy job, they'll say, wait, what? And they'll say that again? Or are you saying this? And they will challenge me and they will ask questions. If I do the same crummy job explaining my work to my next door neighbor, he thinks he doesn't understand it, not because I did a bad job, but because he's not, quote, quote, smart enough. And he won't ask questions. He won't interrupt. But if you talk about Spider-Man or Superman, they don't get the same shields up. And if you can tie it into a narrative, like the death of Spider-Man's girlfriend, Gwen Stacy, and showing how the same physics that operated there explains how airbags can save your lives in an automobile crash. By tying it into a narrative, some people have a better time understanding it. So it's not saying that the way that we traditionally teach is wrong, right? They worked for me. But, there are other people who are interested in this stuff, and this provides a low barrier entry point, is the idea.
So do we have follow-up book like this for relativity?
I just got done with this one. Relativity. Actually, there is in the expanded second edition of the Physics of Superheroes, there is actually a chapter on relativity as it deals with the Flash, who obviously has the ability to run at super speed, so he deals with relativistic corrections all the time.
How big is your comic book collection?
How big is my comic book collection? Did my wife put you up to that? Or as my wife refers to it, the fire hazard.
Time investment in reading all of these comics.
Yeah, it's a sacrifice that I've made for you guys. I read comic books as a kid. I gave it up in high school upon discovering girls. A discovery I'm not given enough credit for in the scientific literature. That's for another time. And then in graduate school, actually, I was waiting for the results of my comprehensive qualifying exam. And I saw a spinner rack saying, "Hey, kids, comics." And I just picked up a handful, and some were terrible, and some were really good, much better than I remembered. And I just kind of went back into the hobby. I have thousands. I don't think of it as a guilty pleasure because I don't believe in guilty pleasures. Right? You like what you like. Snobbery is the public face of insecurity. So, yes?
So, do you ever talk about consciousness and how that...
Do I ever talk about consciousness?
How that comes into, physics in any of your students? I don't know much about
No, the question is, do we ever talk about consciousness? And, not officially. I mean, I work with, as part of my research, I work with neuroscientists. Right? And that's obviously the big enchilada. Actually, it's kind of interesting because one of my colleagues said that at a neuroscience conference, they were discussing this, and they were unsure of where the breakthrough would come from, whether it would be from mathematics or physics or electrical engineering. A lot of signal processing work is being done, chemistry. And they said, one thing's for sure, whoever figures this out, we're going to call him a neuroscientist. He's in our tribe, or she's in our tribe. Consciousness gets to my very issue of faith. Faith, at least the way I define it, is belief in something without evidence. Because if I can show you the evidence, if I can show you the proof, then it's science or reason. It's not, I don't have to believe it on faith. My faith is that everything has a reason, that reason can discern. And I can't prove that that's true, because there's a lot of things that we don't know the reason for yet. But I believe that they can be understood. One of the things that I can conceive it's possible could not be understood is consciousness. Because it's difficult to see, say, Seattle when you're standing here in Microsoft. Right? We're inside the consciousness, so it's kind of hard for us to fully get a handle on it. But I don't believe it. I believe that we will figure this out, that somehow, through these electrochemical interactions, we'll understand what goes on and consciousness. I'm not 100% sure that it will have anything deeper to do with quantum mechanics than simply the fact that it involves atoms. But, so I think Penrose is barking up the wrong tree on that one. But that's me, right? This one, and then that person, and that person.
So is it correct to say that you don't buy the Copenhagen explanation of quantum mechanics? Because
it's kind of funny,
well,
Official interpretation.
I mean, okay.
Well, why don't you...
Okay, so you have asked me to explain Copenhagen explanation in front of a physicist.
You started it. I started. You started it.
To say. That's correct.
No, please continue. This is fascinating. Hey, one thing I learned from reading comic books, you're not a scientist unless you got a pipe.
Okay, Okay, so this is a good experiment then, you know, a layperson's understanding or the Copenhagen explanation of quantum mechanics. My understanding of the Copenhagen explanation of how it is that the probabilities collapse into why you can't both determine whether the electron is in one place or another until you make the observation. I mean, the fact that you can demonstrate, you know, experimentally that this electron has to have been in both places at once before you make the observation. So, you know, you can prove that experimentally, but how do you explain it? You can't explain
Okay, so
it.
here's let me take a stab at this, because there have been some experiments on this recently. This gets to this very notion of quantum entanglement that people are dealing with, trying to develop quantum computers. I said an electron can only have spin up or spin down, right? So say I bring two electrons together and I arrange it so that the net magnetic field is 0. So one has to be spin up and one has to spin down, but they're so close together. Electrons are called fermions because they obey Fermi direct statistics, but electrons all look alike. Okay, that's not the prejudice statement of an anti-Fermite, but it really is true that they're indistinguishable, so it doesn't matter which one is on the left and which one is on the right. So I don't know which one is up and which one is down. But I get them so close that they're now entangled. Now I stretch my infinitely stretchy ribbon, and I bring them across to two ends of the country. And no one breathes, no one disturbs them. Of course, the stretchier it gets, the easier it would be to break the ribbon. Once the ribbon's broken, what's done on one end has no communication with the other. Now, it's not the fact that once I measure and see that this one is up, I instantly know the other one's down, because that's just logic, right? I knew that the total had to be 0. The thing is, I pulled a fast one on you through the whole talk. Up or down compared to what? We're in a room, so we think of up and down this way. But it has a magnetic field, and it's up and down relative to the magnetic field that I put on. If my magnetic field's pointing this way, this is going to be the up and down direction. If the magnetic field is pointing this way, this will be the up and down direction. That's the information that gets transferred. Because it's not just that one is pointing in one direction and the other is in the other, but once I do the measurement, it then creates a direction, and that information is instantly transferred to the other end of the ribbon, because it's basically the same wave pattern. It's just the same ribbon. So that's the part that Einstein called the spooky action at a distance. And because it opens up the possibility of faster than light communication, because it's the same wave, and so what I do to one suddenly, and that's where these collapsing wave functions and all of this stuff comes in. The really disturbing part, experiments seem to show that that's right. Right? Recent experiments. There's this nice book out on quantum entanglement. Zeilinger, I'm butchering his name, I apologize, but by the guy who actually does.
The lightness of being? Is that the book you was?
No.
No.
Yeah. But this is a popular book on quantum entanglement that just came out. After you buy my book, you can buy that one. But that's in these issues. But it's been only recently that we've been able to experimentally probe this. So up until then, it's been in the realm of more philosophy. Once you start interacting with the outside world and you jiggle, you break the ribbon, then measuring one end doesn't do anything to the other end. That's called decoherence. That's the world that we live in. That's why I don't believe this coherence entanglement has anything to do with consciousness, because your brain is at 98.6 degrees Fahrenheit. The atoms are jiggling so much that any coherent wave pattern gets destroyed. There was in the back.
So, yeah. Sort of segueing off of that, actually talking about consciousness.
Could you speak up, please?
Sure. So sort of segueing off of consciousness, and I don't want to get too much into philosophy, but what implications does that have on the discussion of free will?
Who else has a question? I don't. There's a lot. I'm just like a humble guy in a lab, I'm happy if I can get nanoparticles in my semiconductor because the NSF has a rule that every grant proposal has to have nano in the title. And so,
Maybe 2 more questions.
sure, I can answer questions as long as people want. But there was someone back there, and then I'll get to you. In the blue sweater. Well, did you have a question?
Yeah, I'm sorry. Has anybody been able to modulate anything that was quantumly entangled and measure it?
Yes and no. Yes, I mean, yes. I'm upset with myself for not remembering exactly how to pronounce this guy's name. Zeilinger, the guy who wrote this book that I just mentioned, has entangled pairs of photons, sent them through fiber optic cables so that they're equivalent of 17 miles apart, measured the polarization of one at one end, and it determines the direction of polarization of the other.
But that's only knowledge that's going into it.
Oh, no. It's absolutely. The only thing that's getting teleported is information. That's exactly right. But it's real information, right? I mean, in terms of that, we know that it's circularly polarized, and the other is circularly polarized in the other direction, but it relative to what axis is not determined until you do the measurement, and then the other one gets instantaneously determined. But that's information. It's real information, though. It's not just logic. It's not just saying spin up or spin down. It's like the electron case.
So
it's up or down relative to what? Yes, sir?
So when they did that, how did they actually change it to see that it changes on the other side?
They prepare the states in different ways. They can pass it through magnetic fields that rotate the polarization. There's a lot of clever experiments. I'm not an expert on all of that I can tell you off the top of my head, but there are ways of actually getting at that.
Are you saying that you can flip one and the other one will flip?
Well, not only that, but again, the point is, if I measure it and find that this electron is pointing this way because this is the magnetic field that I put it on, then the other one is pointing in the same direction. Well, that's not trivial, right? Because I could have done it, if I did it this way, then it would be down this way.
You can't do anything to the other photon.
They're spatially separated.
But once you've measured it, then they're not entangled anymore.
Oh, absolutely, yes. That is correct.
And you change the direction of this one and know that this one has instantly changed the opposite way.
Well, no. Once you measured one, that determines what the other one is doing. Yes,
It's knowledge, not information. It's not
information.
No, I think it is information because I can set a binary code. Magnetic field this way is a 1. Magnetic field this way is a 0. And so I could then transfer a 1 or a 0 across the country, whether it's faster than the speed of light or not. Experts disagree, but I can transfer information, 1 or 0. Well, yeah, the process of doing that collapses all the different, because it has an infinite possibility of which direction it points in. As soon as I do the measurement, it's now pointing in the direction I measured. But so is the other one, even though I can come back the next day and measure it and find that it's still pointing in that direction. That's the thing.
One more question. Yeah, so I'm glad you talk about graphite.
Graphene?
Yeah, so reading for the laymen in Microsoft, we are reading this news about Nobel Prize. And then I think the news actually suggests that he was using some napkin or something, some material to manipulate all this graphite with one layer, scotch tape or something.
Yes.
With one layer of the atom, it's just incomprehensible. Maybe you can shed some light on that. Does your book say anything about that?
It talks a little bit about graphite. I think the graphene was a little bit of a premature Nobel Prize, but of course, this is coming from a little bit of sour grapes. I thought for sure this was going to be my year. I gave $50 to every member of the committee and a C note to the chairman. Told my wife, "Ooh, we better go to sleep early. We're going to get that 2 a.m. wake-up call." Money down the rat hole. Anyway, the idea is that you have, carbon wants to form 4 chemical bonds, right? In diamond, it forms 4 equally strong chemical bonds in a tetrahedron arrangement. If you look at these atoms, each one, the average number of neighbors, closest neighbors is 3. So it's got 3 very strong chemical bonds, but there's a layer above it and a layer below, which means that it's got, like, in essence, half a bond above and half a bond below. So in the plane, very strong bonds. Out of the plane, very weak bonds. So yes, you can peel it with Scotch tape, and you peel, and you take the piece that you had, and then you peel it again, and you peel it again. You're peeling the material off layer by layer when you just write with a pencil. And here you're just using Scotch tape, and you're just cleaving the crystal. And you keep doing this until you get lucky, and you can get a layer, very small, that's only 1 atom thick. Now, that's not what's so cool about graphene. What's cool about graphene is that the 3 electrons that are in the bond, I don't care about them. They're bonded up. That 1 electron that's now not attached to anything, all of those electrons are standing up out of the plane like posts in a field, and all of those can overlap. And for a very technical reason, the electrons in this broadened out 1-seat band move as if they were like relativistic massless particles. The equation that describes it is the relativistic version of the Schrödinger equation, called the Dirac equation. And also, depending on how it overlaps, if you look in one direction, it will look like a metal, and in another direction, it looks like an insulator. It's got all sorts of cool electronic properties that, get into the weeds, though, and are much more advanced.
That's a good application.
Well, the idea is that the electrons, yes, that if they move as if they were like massless relativistic particles, that they move very fast. So you'd have very fast transistors. Since this is so strong and 98% of the light passes through it, it'd be great for making an invisible force field. Because you couldn't see it, the light would pass through it, and you go, oh, there's graphene there.
So now with the Scotch tape, you take out.
Sure. Well, but you peel it apart. If you wrote very lightly, you might actually be able to get a little layer of graphene with your pencil.
I'm going to let you guys all ask him questions as you get your book signed and say hello. I do want to